question A8 then from the 2012 Advanced Higher Applied Maths Mechanics. A 10-mark question, the biggest number of marks so far, and it's on vector motion. Now, it's only got 3 marks for this first part, and this first part is going to be so tedious. What it does is this, it says, a particle P is projected so its position vector is given by this. So it's got the 2 independent parts of the motion given parametrically in terms of the time. Now that's the horizontal motion. Notice that's going to represent an acceleration. That distance is increasing for uniform time intervals. The vertical motion is steady. Like it's got a velocity of 4. So it means it's accelerating across the way but travelling up at a steady speed. So it's going to follow a path like this, like a square root path. Anyway, that doesn't really matter here. What's this? That's that first particle. Now another one is set off as well, a particle Q. And all it says for particle Q is it's got the same acceleration as particle P. So for particle Q, all I know that it's acceleration. Now there's different sorts of notation you can use, but I'll just stick with this. So A of Q, meaning the acceleration of Q, is the same as the acceleration of P. Now, there are other bits of notation I could have used. Instead of R of P, I could just have called that P for the position vector of P. And the velocity I could just have said is P dot, being the standard for dP by dt. And for the acceleration, P double dot. And similarly for Q. And that might have been a bit quicker, but since that's what you'll see in the marking scheme, I'll use that. However, for the rest of the question, just to save a bit of the tedium, I'm not going to keep expressing them in terms of the full linear combination of the unit vector, base vectors. For this, I would just write it down as t squared plus 3, 4t. Just putting it in component form, just using a row vector to represent that. But when I get the answer, I'll put it back again. It just saves a little bit of writing. Anyway, the acceleration is to be the same, and what does it say? It tells you at a time t, it tells you more information about q. It says the velocity of q, so I'll use that. The velocity of q is, I'll put it all down, negative 4I plus j at t equals 0. And similarly at t equals 0, the position vector is 8j. Now, if it was just a one-dimensional case, for instance, just travelling in the horizontal direction, then you would just have an expression for x in terms of t. The velocity, or I should just say speed in one direction, would be dx by dt, and the acceleration would be differentiate again. And if it happens with the acceleration I wanted to go backwards, well then I would just integrate that. It would be the integral of a dt, and then x would be the integral of v dt. Remember, of course, that they're going to introduce constants that will need evaluating. And the only difference here is, instead of having one equation, you've got 2 equations, one for each component. And these are perpendicular to each other. These are independent motions. They might be tied together by their common parameter t. Those are parametric equations. But once the 2 of them at a given time are brought together, they're going to give a resultant. But as far as the integrations and differentiations are concerned, you've just got 2, if you like, independent equations to integrate and differentiate. So, starting it off, if you've defined the position vector of q, I'll get that from the acceleration of q by integrating twice. But I won't get the acceleration of q until I know the acceleration of p, because it's the same as that. And I won't get the acceleration of p until I've differentiated it twice. And this is all for 3 marks. And there's all this notation, that's why I'm not going to put down the i's and j's, I'll abbreviate it a bit. So what I've got so far is this. The position vector of p in component form is that. So if I want the velocity of p, I'll differentiate it. I don't think I need to make the statements, it's only 3 marks. So that would be 2t4. And if I want the acceleration, I'll differentiate it again, so it'll just be 2, 0. So that means that the acceleration of q is the vector 2, 0. Notice that's just 2i, if you like. I'm not going to put this until the end. Now that means that the velocity of q will be the integral of that. And I'm not sure if it should start showing that now. The integral of 2, 0 dt. Because that's going to turn into two parts. It's going to turn into 2t plus a constant, and that 0 will go to some other constant. Now I think in the marking scheme using the vectors, they've called that the original vector. So they've got the integral of the original vector, and the result of that they've produced some constant vector. So the integral of that, they've ignored this part here and just got it as like 2t0 plus a constant. And then evaluate the constant, but then you just have to add it back in. I think it's clearer just to introduce the constant into the two independent parts. Now, but there's an evaluation. You know that when t is 0, if t is 0, then this becomes c1, c2, and that should equal negative 4, 1, which means it's equal to 2t, so c1 must be negative 4, and c2 must be 1. And then we can get down to r of q. R of q will be the integral of that, the integral of 2t minus 4, 1 dt, which will be t squared divided by 2 minus 4t plus another constant, I'll call that r3. 1 will go up to t plus another constant, call that 4, c4. And at t equals 0, it told you here, when t is 0, that's c3, c4. That should equal 8 j. That's a 0, 8, which means it should equal t squared minus 4t, and c3 is 0. T plus c4, which is 8, 8. So here's my final answer. For 3 marks, RQ is going to be, and I'll just put it back into that using the unit base vectors there, t squared minus 4ti plus t plus 8 j. Now that was a lot of palaver for 3 marks. Even worse if you had to set it all out with writing in the extra 2ti plus 4j, etc. And the 3 marks were sparsely distributed as there was 1 mark for getting the acceleration, the vector of the acceleration, there was 1 mark for finally getting the velocity, and there was 1 mark for finally getting the position vector. But some of these will be needed again in later parts, so these marks are getting doubled up, if you like, later. Now part B, the time taken from the start of the motion until the particles are closest to each other. Well, there's a couple of ways you could do that. Closest to each other, the distance between them. There's the particle P and the particle Q at a given time t. Find an expression for the distance between them, and then find when that expression has its lowest value. Well, the distance between them will be the length of that vector PQ. You get the vector PQ and take its magnitude. Now, P, because PQ will be the position vector of Q minus the position vector of P. So I'll do that, find that. So PQ would be, oh, we're not using Q minus P, we're using RQ minus RP. That didn't need to be a wee thing, that's just getting quite messy. Which would be t squared minus 4t minus t squared plus 3 for the first component. Oh, maybe I'll just concede and call that the first component, you'll have to go. Plus t plus 8 minus 4t for the components of the j component. Tidying that up, that gives you, well, luckily t squares disappear, notice that. So you've got negative 4t minus 3. Of course, that could have been positive if you did it the other way around and found QP. But that makes no difference because you're going to square it anyway. And maybe it balances on this side. No, it doesn't. T minus 4t is minus 3t. And then plus 8 j. However, it's not the direction of the vector that I want, it's the magnitude of the vector that I want. So these signs won't matter in the end. So the magnitude of the vector, but just keep it squared rather than having to have the square root, will be that squared plus that squared. It'll be negative 4t minus 3 squared plus negative 3t plus 8 squared. Yeah, you'd probably have done that as well, going PQ, so it would have been Q minus P. Multiply that lot out and see what it comes to. Well, square the first, square the last, and the middle twice the product. Luckily, all of that's going to turn out positive, isn't it? So it's going to be 16t squared plus a 9, 12 plus 24t. This one here, again, it will be plus 9t squared plus 64, but that'll be minus 24 doubled, 48t. So that then comes to 25t squared minus 24t plus an annoying 73. Now, you have to find when PQ's at its smallest, but that's the same as saying when the square of the distance is its smallest, so you don't have to find a square root, for instance, here. So when is this at its smallest will give the same result. Can you see what you've got here? That's a quadratic, that's a parabola, it's got a smallest value. So you can either complete the square, find the smallest value, or just differentiate. And you can just differentiate the squared expression. That's perfectly acceptable. And instead of this whole expression here, I think I'll just call that PQ squared. So if you differentiate that with respect to time, you're going to get 50t minus 24, and that will be at a stationary value. Stationary value means that 50t minus 24 is 0, which means that t equals, it's not very neat, 24 upon 50 seconds. Or if you like, doubling the two parts, 0.48. 0.48 seconds. Now you might have been able to get this little expression here as the derivative of this with slightly less arithmetic, maybe not an awful lot less, if you just differentiated this straight away as the function of a function. So we'll try that. So this dp, this will be into this bit here now then, equals this as well. So it would be 2 times the bracket power 1 multiplied by the derivative of the bracket, which is a negative 4, plus 2 times the bracket power 1 multiplied by, in this case, negative 3, the derivative of the bracket. So that would be, in this case, we've got 8 4s are 32. So you've got 32t, and that's again going to be plus 24. And this side here is going to be again plus, and that's 6 3s are 18t, but that will be minus 48. And when you tidy it up, it comes back to that again. So that might have been a wee bit quicker. Now there is another way. So there's another way, which is to consider the relative motions. You've got the points P and Q moving along. When are they closest to each other? One way of doing that would be to travel with one of the points, like to travel with point P and observe Q relative to you. So instead of them both travelling, it's effectively you're static at P, take P's frame of reference and watch how Q moves relative to you. Notice it could be a pattern like this, coming closer and away and closer behind, sometimes forward, sometimes. If you were static at P and watching Q, you'd be at the closest point when the relative distance to Q, which of course will come away and towards you, like travelling along 2 tracks that are bending in and out. You've got the relative position of Q, which will just be the position vector PQ. And if you think you're steady at P, Q will appear to be have its direction changing, its velocity changing relative to you in different directions. That will be the relative velocity compared to you. And you'll be at your shortest distance when that's a right angle. It'll not be travelling away from you, it'll not be travelling towards you, it'll be at right angles to you. So you'll be at the closest point when the relative position is perpendicular to the relative velocity. And of course the relative position would be Q minus P, and the relative velocity would be its velocity minus your velocity, VQ minus VP. So that's what we'll have then. We'll have, whoops, have to use those R's, don't we? RQ minus R, I keep doing that because I'm used to doing position vector, RP dot, because I want the perpendicular one, I want it to be perpendicular, VQ minus VP to equal 0. Straight away, that's going to be full of all those negatives, isn't it? Taking it from that point of view. Maybe I should have stood on point Q and watched point P dance about instead. Ah, what's a few negatives? Well, they're annoying, that's what they are. Anyway, right, what have we got for this bit then? RQ minus RP. So, I've got this already in that other part, but I've not got it to hand. So this take away this, that take away that would be 0. So I've got negative 4t take away 3. Negative 4t, keep on doing that. Negative 4t take away 3. Oh, I'll just call it I. And for this component, it's going to be t plus 8 take away 4t. So that's a negative 3t plus 8. Dot. Now the velocities, they were in the other part, so you could just have copied that down. That's where those marks would have been there in part A. But I'll just have to put them down again. So what is the velocity of Q? There, I did it there as well, because you're used to writing Q for the position vector. That's just going to be 2t minus 4. And that's just going to be 1. I'll just emphasise it by putting a 1 j. And what's the velocity of P? Well, that'll be 2t just of I, and that'll just be plus 4 j. So what's the relative velocity? This take away that. So that'll be a negative 4i. This take away that. That'll be a negative 3j. And all of that should come to 0. Now it's just a case of do that multiplication. And the only ones that matter are I dot I and j dot j, because they produce a 1. Because the mixtures, the perpendicular ones, produce zeros. So I've got a negative 4 times this. Negative 4 times 4t minus 3. Minus 3 times this one, negative 3t plus 8 should equal 0. So what's that? Negative 16t plus 12 plus 9t, positive 16t, plus 9t minus 24 is 0. 25t minus 12 equals 12. So there again, t equals 12 upon 25 seconds. 4 times both parts, 0.48 seconds. It's a wee bit more sophisticated, just travelling with one of the points and observing the relative position and relative velocity of the other one to find when you're at the closest approach. Completely forgot to mention the marks, of course, for part B, because there were 4 marks there. They were just spread out evenly throughout it all. I think they just write it out and then just go, oh, 1 there, 1 there, 1 there, and 1 there. Anyway, what's this part C? The time at which the particles are moving at right angles to each other. Well, that's 3 marks as well. When you compare it to that last bit for 4 marks or that first bit for 3. When are they at right angles? There's the 2 motions. There's the 2 velocities. When are the right angles? Is when the scalar product's 0. Right angles means that the velocity of P times the scalar product with the velocity of Q should equal 0. And that gives you a mark. So that would be 2ti plus 4j dot 2t minus 4 I plus j should equal 0. Scalar products, just the I dot I and the j dot j. So 2t times 2t minus 4 plus 4 times 1. I'll just put that down. So that's 4t squared minus 8t plus 4 is 0. Take out the common factor, leave it in. I don't need to maintain the value of this expression. So I'll just make it t squared minus 2t plus 1 equals 0. And there's a wee square. T minus 1 squared equals 0. So just t equals 1 for that double root. So that'll be statement. Perpendicular after 1 second. And the marks were knowing the scalar product should be 0, getting the quadratic equation, and then solving it. 3 marks. 3B easy marks.